A Mullard radiant screen television tube begins on the drawing board after long consultation between research, design and commercial engineers. From these preliminary drawings and accompanying specifications, component parts are made up and assembled into a prototype tube. In the meantime, the engineering department is designing and making jigs, tools and machines which will be required for quantity production of the tubes. Here a precision-engineered jig is being gauged to give the accuracy which will be required when assembling the electron gun. Pre-production runs prove the tools and the final design, and simultaneously engineers work on the problems of the handling and flow of materials and the most efficient methods for assembling and processing. Among the many tests applied at this stage is the measurement of spot size and brightness. Here a pattern of dots is examined under a microscope, and here picture brightness is measured accurately by a photoelectric device. Tubes from the pre-production run are also submitted to life tests, and only when all tests have been satisfactorily concluded does the main production begin. A necessary preliminary to production is establishment of quality control to prevent unsatisfactory materials reaching machines or operators. In this way, machine time and operator skill are not wasted. Upper and lower limits of size and performance are set for each stage of manufacture, and these limits are never exceeded. Actual manufacture starts with the bulb. This is made in three parts: the face, the cone, and the neck. The cone sections are gauged for size and examined for bubbles and other blemishes. The face plates are inspected and gauged in a similar way. Glass tubing is cut into lengths to form the neck. These lengths are placed on a machine and the ends are fire polished. Each neck tube is flared at one end so that it will exactly fit the cone. When cool, each neck is gauged to check its dimensions. Now the neck is fused to the cone on this machine. On another machine, an electrode of nickel-chrome iron is fused into the side of the cone. This is the EHT connection to the tube. In this oven, the cone and neck assemblies are annealed to ensure that there are no stresses left in the glass. Meanwhile, the faceplates are being preheated in another oven prior to joining them to the cone. This is the machine on which the face, cone and neck come together to form the complete bulb. See how the gas jets move in and out to follow the contour of the bulb. Now the complete bulbs are annealed by raising them to a certain temperature and cooling them very slowly. This removes any stresses which would be a source of weakness. At the other end of the machine, and before further processing, each bulb is inspected. The inspection includes examination under polarized light to check that the glass is now free from stresses. Next in the sequence of operations and processes is the laying of the luminescent screen on the inner surface of the faceplate. The screen is composed of a mixture of chemicals which emit light under electron bombardment. And because picture quality, brightness, and even tube life depend upon its composition, it is the subject of continuous research. In the Materials Research Laboratory, every batch of screen powder is scrupulously examined and tested. This chemist is determining the size of the particles in a sample of screen powder. The actual size is in the order of thousandths of an inch. Here, tests are being made on the adhesive qualities of a screen which has been deposited on a glass slide on the bottom of a beaker. In another test, a miniature cathode ray tube is specially made to check an important characteristic of the cathode ray tube screen. When a beam of electrons strikes the screen, secondary electrons are ejected from the screen material. For good performance and long life, the number of secondary electrons must be greater than the primary electrons reaching the screen. The miniature tube is fed with a pulsating signal, and both the primary current and the secondary current are indicated simultaneously on an oscilloscope. You can see the two pulses on the oscilloscope, the one being larger than the other, showing that the secondary current is greater than the primary current. There is the same care and attention to detail in the actual production process of screen laying. The first step is to ensure that the bulbs are perfectly clean and free from any trace of grease or other foreign matter. This ingenious rotary machine washes each bulb successively, first with a weak solution of hydrofluoric acid, then with tap water, and finally with specially purified water. From the washing machine, the bulbs are transferred to the conveyor belt, where the process of screen laying takes place. In these large tanks, the buffer solution and the water glass, which are used to deposit the screen on the inside face of the bulb, are prepared. These solutions are then piped to the beginning of the screen laying belt. The buffer solution is poured into the bulb. A quantity of luminescent powder suspended in the water glass is now prepared. This is introduced into the bulb through a rose, which distributes it evenly throughout the buffer solution. As the tubes move along the machine, the luminescent material gradually settles as a deposit of uniform thickness, which is held to the surface of the glass by a gel-like formation produced from the water glass. When the screen material has settled, the bulbs are automatically tilted so that the clear liquid runs out, leaving the deposit undisturbed. The bulbs are now conveyed to the drying machine, in which warmed and filtered air is gently blown into the bulbs while the external surface is heated by infrared lamps. Every bulb is now inspected under ordinary light and under ultraviolet light to check that the screen is of adequate and uniform density over the whole area and free from blemishes. A coating of graphite is then applied to the inner surface of the cone and neck. This coating will form part of the electrical connection between the final anode of the electron gun and the EHT terminal on the side of the cone. The graphite is dried by jets of air. Then the volatile constituents of both the screen material and the graphite are driven off in this continuously heated oven. Now, once more, the bulbs undergo an inspection for screen and glass faults. And after this, they are ready for the electron gun. But before we continue along the production line, let's step aside to see some of the many controls applied to secure high quality. Back in the Materials Research Laboratory, every batch of material issued to the production line is carefully tested. In this section of the laboratory, glass, metals, screen powders, cathode material and graphite pastes are analyzed and tested. Here we see tests of hardness and tensile strength on metals that are to be used in the electron guns. And here the efficiency of screen powders is being measured. Other tests employ such equipment as the spectrograph, in which the composition of a material is indicated by the color of the light it emits when incandescent. Analysis is also made by diffraction, using both electron diffraction cameras and X-ray diffraction cameras. Now we come to what may be called the heart of the picture tube, the electron gun. The various component parts of the gun are made to the highest standards of accuracy, for upon this the satisfactory performance of the tube largely depends. Here is the gun for a 17-inch tube, and with it the precision components from which it has been assembled. These components include the cathode, a nickel tube, the closed end of which is coated with emissive material, the heater, a fine spiralized tungsten wire coated with an insulating layer of alundum. The heater is inserted in the cathode tube. In operation, an electric current passes through the heater and raises the temperature of the cathode so that electrons are emitted from its emissive coating. This is the grid, which has a small central aperture through which the electron beam passes. The television signal is applied between the grid and the cathode to modulate the electron beam to correspond to the light and shade of the various parts of the picture. There are 3 anodes with small central apertures. When assembled and in operation, they cause the electrons emitted by the cathode to travel along the tube at very high speeds. This is one of the getters, which, after the bulb has been evacuated, is volatilized to form a deposit on the side of the neck. These springs form the electrical connection between the final anode and the EHT terminal via the graphite coating on the inner surface of the glass bulb. Here the springs and getters are assembled, ready to be mounted on the end of the gun. These are the components which make up the glass foot. A glass ring, a short stem of glass tubing through which the air is pumped out of the bulb, and a number of connecting wires. Here in the factory, we see these components being loaded onto a machine where they are joined. First, the glass stem, next the connecting wires, and then the glass ring. They move round on the machine and are gradually heated in gas jets, the temperature being greater in each successive position. The 2 glass components melt and fuse into each other and form airtight seals around each wire. The metal of the wires has the same order of coefficient of expansion as the glass, so that when the foot is heated or cooled, the metal and glass will stay in contact and no leak occur. Finally, the wires are reduced by hydrogen to clean off oxides formed on their surface. As the feet come to the end of the machine, they are transferred to another, where they are annealed to ensure that no stresses are left in the glass. Now we see how the components of the gun fit together. First, the grid assembly, anode 1, anode 2, and the anode 3 bush. These are joined together. Next, the cathode mica assembly. Anode 3 and heater are added. This assembly is then welded to the foot. And finally, the collar diaphragm assembly, which includes the getters and springs, is added to complete the gun. In the factory, the guns are assembled in a number of stages, each operator being responsible for a limited number of operations in which she is expert. The positions and distance of the components of the gun relative to each other are extremely important and must be made accurate to within fine limits. To ensure this accuracy, jigs and distance pieces are used throughout. Each stage of assembly is a precision operation in itself and requires great care and delicate handling of the components. Checks are made to ensure that there are no short circuits between any of the electrodes, and the positioning of the components is examined under a magnifying glass. The completed gun is greatly magnified in this instrument, and any final adjustments can be accurately made. Now, after washing to remove any grease or small particles, the guns are ready for sealing into the bulbs. The gun assembly is mounted on this automatic machine. The bulb, which has been washed out with inert gas, is placed in position, and the gun assembly, the glass foot of which has been preheated, is automatically located correctly in the neck of the bulb. As the tube rotates on its axis, it also moves to successive stations where gas flames soften the glass at the point of junction between the gun mount and the neck. As the neck and foot fuse together, the excess glass falls away. The sealing in completed, the next stage is to pump the air out of the tube to form a vacuum. Each tube is mounted in its own pumping unit or trolley. And passes into this huge heated tunnel. During the time it takes to pass through, the air is continuously evacuated through the short glass stem at the base. While this is going on, the whole cathode ray tube is heated to help drive off occluded gases, and current is passed through the heater to heat the cathode. This causes chemical changes in the emissive coating on the cathode, the original coating of barium and strontium carbonates being reduced to barium and strontium compounds having emissive properties. On emerging from the pumping plant, the degree of vacuum is checked by measuring the ionization current through the tube. Finally, heat is applied to soften the pumping stem so that the tube is automatically sealed off. Now the getter is fired. It is heated by eddy currents until it evaporates and forms a deposit on the side of the neck. Any residual gases in the tube and any released during life are absorbed by this deposit, so maintaining the vacuum. The base cap with its connecting pins is now fitted, the lead-in wires being threaded through the hollow pins. Cut to length and soldered to the end of the pins. An electrically heated cover is put on the base of the tube, and as the tube travels along the conveyor belt, the cover bakes and hardens the cement, securing the base to the tube. During its travel, the tube is also aged by operating it under controlled conditions. This causes other chemical changes in the cathode material, which result in improved emission. After aging, the tubes undergo a series of severe tests laid down by the Quality Control Department, and every tube must pass all of these tests. They include tests on insulation resistance between the electrodes, vacuum, heater current, evenness of illumination and color behavior at overvoltage, point of cutoff, and uniformity of cathode emission. In addition to these electrical tests, every tube is given a complete physical examination to make sure it conforms to specifications laid down for every Mullard tube. The external surface of the tube is now coated with graphite. This coating, together with the glass of the bulb and the internal graphite, forms a capacitor, which may be used as part of the smoothing circuit of the EHT supply. This graphite is dried in a tunnel where the tubes are heated under infrared lamps. With the marking of the type code, the actual manufacture of the tube is now finished. But once again, every tube is thoroughly inspected. Even this is not enough to satisfy the Quality Control Laboratory. Finished tubes are taken at random from the end of the production line and subjected to more than 40 laboratory tests. By comparing the results of tests on successive batches, any trend away from normal is quickly detected and reported to the production department, so that steps can be taken to rectify matters before quality is adversely affected. Many of these tests are similar to those you have already seen. Others are specially designed to check the performance of the tube under service conditions. This tube, for instance, is being given an underheating test to see how it would behave in a district where the mains voltage is low. And here, a tube is being operated under conditions which produce an image of the cathode on the screen. Examination of this image shows whether the emission is uniform over the whole cathode surface, an important point for picture quality and also for cathode life. A proportion of the tubes is submitted to tests to ascertain their expectation of life and to reveal the cause of ultimate failure, no matter how long life may be. To speed up these tests, the tubes are run at excess EHT voltage and excessive beam current, so that in a few months they have done the equivalent of several years' normal service. Service conditions are simulated by switching the tubes on and off at intervals, and once a week each tube is taken from the rack and its characteristics rechecked. So, as you have seen, in the production of Mullard radiant screen television tubes, nothing is left to chance. Every stage of manufacture is critically controlled, and continuous research enables the most advanced techniques to be adopted without delay. This constant urge to achieve perfection is your assurance of the consistent quality and long life of Mullard radiant screen television tubes.